morning, friends. I am here for my course, Engineering Thermodynamics. I am in the module 4, which is about power cycles. Once we talk about the power cycle, it means the cycle which either produces the power or it absorbs the power. In this process, I have covered the 3 cycles which are power producing cycle like Otto cycle, diesel cycle and dual cycle. Today I am in the next cycle, which is the Brayton cycle. In all these 3 cycles which previously I have covered, we can see one thing common is that the heat rejection is at constant volume process, that is isochoric process. Because in the piston engine, this isobaric or constant pressure heat rejection is somewhat difficult, as this will increase the size of the cylinder and hence the weight and other complications will be increasing. To avoid that, a constant volume or isochoric heat rejection is undertaken. We have seen that in Otto cycle the heat addition is at isochoric or constant volume process, but in diesel cycle the heat addition is at constant pressure process. Seeing this 2 cycle, the 3rd cycle was adopted, which was the dual cycle, and in the dual cycle the heat addition was in the 2 processes. First one is at constant volume process and the second one is constant pressure or isobaric process. We have seen in the previous lecture, I have discussed that at the constant volume heat addition is somewhat difficult because at instant of time, at the very friction of second, in nanoseconds, your fuel to burn. That is not possible in the real scenario. So fuel will start burning and it is taking some more volume or it is not at the constant volume. By this situation, the Rudolf diesel has developed its own cycle, which is called the diesel cycle, and the diesel cycle was developed in that the heat addition or the burning of the fuel is at constant pressure process. So it takes some time to burn the fuel and the burning is quite good. Taking in this consideration, the 3rd process was developed, that is the dual cycle. In the dual cycle, some part of the fuel is burned at a constant volume when the piston reaches to the top dead center or near the head. And after some part is burned, the another part will burn taking the some constant volume, constant pressure. In that some volume will be displaced. So better results we could obtain comparing to the diesel cycle and the Otto cycle. Because in diesel cycle also it takes a lot of time for burning of the fuel. So that much stroke volume is not used for expansion of the gases. Keeping in this mind, another cycle was developed. In this cycle, if you see, the compression is isentropic process, heat addition is at constant pressure process like diesel, your expansion is also isentropic, but here the heat rejection is also at a constant pressure process. In this, Brayton has developed the cycle and we are going to discuss about the Brayton cycle in my today's lecture. In today's, I will be discussing about introduction to Brayton cycle, early Brayton cycle, early gas turbine cycle description, efficiency of the Brayton cycle or the Joule cycle, efficiency derivation, condition for maximum work done, and the efficiency. This I will be going to take. So here in the introduction part of the Brayton, and this Brayton cycle is also known as the Joule cycle. The engine cycle is named after the George Brayton. His period was from 1830 to 1892. The American engineer, the Brayton was an American engineer who developed it originally for use in piston engine. He has made this engine for the piston engine, but afterward this was used for the gas turbine engine because in the piston engine it was not very much success. The Brayton cycle is a thermodynamic cycle that describes the operation of certain heat engines that have air or some other gas as their working fluid. So in this, we can use air or some other gases also as a working fluid inside the piston and inside the cylinder. The original Brayton cycle engines used a piston compressor and piston expander. So in this, we use a separate compressor, piston and cylinder, and the separate expander piston we are to use. Modern gas turbine, GT engines and air breathing jet engines also follow the Brayton cycle. So we will see in the next slide that how the historical development of the gas turbine is taking place. And after this Brayton's development of the piston engine, this same cycle was used for the power cycle of the power generation, electrical power generation, for the turbine engines, for the aircraft gas turbine engine, and so on. Although the cycle is usually run as an open system, conventionally assumed for the purpose of thermodynamic analysis that the exhaust gases are reused in the intake, enabling analysis as a closed system. So we are assuming that whatever gases are coming out of after the turbine, we are again using as input, and so we assume that it is a closed cycle. However, in the real practice, it is an open cycle. So here, early Brayton engines, which were developed by the Brayton in the principles of the Brayton, and here this you can see, we have the compression system is different, and this is expander. This is the expander, and this is the compression. So in this 1872 Brayton gas engine, it is called the Brayton gas engine. Then Brayton walking beam engine in 1872, another engine was developed. Brayton engine in 1875, Brayton ready motor, it is called. Then Brayton double acting constant pressure engine. This is shown all the parts here, how this engine was developed, and all the parts of the engine was shown, and it was developed in 1877. Now in 1889, Brayton 4-stroke air blast engine. Here the air was blasted, and with a high compressed air was used in this 1889. And the next year, Brayton 4-stroke air blast engine was developed in 1890. So these are the few piston engines which were developed in the cycle, in the principles of Brayton engine, and they are not very much success in automobile and all because their size is very big. This you can see, very big wheels are here, all these things, but it can be used for the power generation and other stationary work. This I have taken from this reference from the Wikipedia of the Brayton cycle. Now I will go for the next topic, which is early gas turbine history. This history says about how the gas turbine were developed and how the Brayton cycle was used for the modern gas turbine engines. So the first patent was done by John Barber from UK in 1791 first gas turbine patent was filed. Then we can see that in 1904, an unsuccessful gas turbine project by French Stolz in Berlin, Germany, first axial compressor. In this, unsuccessful, but he has made the first prototype of axial flow compressor. Then another type of compressor that is called the centrifugal compressor. In 1906, gas turbine was made by Armand God Limanle in France. Centrifugal compressor was used, but no useful power. That was the basic right, but not useful power we could not get in 1906. Then 1910, first gas turbine featuring intermittent combustion. So first gas turbine with intermittent combustion. It was not a constant combustion. And the person who has developed this is Holdsworth 150 kilowatt constant volume combustion, like auto combustion. Like auto combustion, a constant volume combustion was done. Then in 1923, first exhaust gas turbochargers to increase the power of the diesel engine. So your turbocharger means, again, it is like a turbo engine only, or gas turbine engine, and this was used not a separate engine but to increase the efficiency of the, or increase the power of the diesel engine. In case of a high altitude or in the low density zone, we can use this turbocharger, and these turbochargers are nowadays used for the costly cars, those who are operating in high altitude in India, like Ladakh, Aeronautical Pradesh, Jammu Kashmir, and all the hilly area where the altitude is high. To operate the vehicles, we need the turbocharger, and these turbochargers will compress the air before entry into the combustion chamber. So that was the purpose for this. Finally, in 1939, world first gas turbine was made to power generation by Brown Boveri of Switzerland. Brown Boveri and Neuchâtel, Switzerland. It was in 1939. This engine was developed. Now I will discuss about Brayton cycle description. What are the parts, what are the components, and how this cycle was to be developed. So here in this we have first adiabatic process. The compression is adiabatic. This adiabatic is also, it is a reversible adiabatic. So it is called isentropic. Isentropic process. Isentropic process. Okay, next is isobaric process. So this compression is isentropic process. Heat addition we are doing at isobaric, like your diesel engine. So at a constant pressure we give the fuel, we will burn the fuel. Heat addition means adding fuel which burns. After burning of the fuel, you will get the heat addition in the system. Then we have the adiabatic process, that is expansion. This expansion is also isentropic. Isentropic expansion means it is a reversible adiabatic process. It is not exactly adiabatic, but you can say it is a reversible adiabatic process. So expansion of the gases where the work is done. Work is produced in this. Work produced. Work absorbed. So in the compression process, work is given, and in the expansion process, work is obtained. So that is the difference between these two processes. And the heat rejection. Here, it is isobaric heat rejection, means at constant pressure. Isobaric means constant pressure heat addition is given. Now we have here the diagram. First I will explain the component of the Brayton cycle, and it is a gas turbine engine. So these are the gas turbine engine. And this is the reference which I have taken from the Wikipedia. So here we can see that basically we need three main components. First one is the compressor. Next one is the combustion or combustion chamber. Third one is the turbine. And we need some connections to join. In combustion chamber, we have to supply the fuel here. And in turbine, if you see the shape of the compressor and the turbine, air is entering from 1.1, and here the pressure and the temperature is up approximately atmospheric. P1 and T1 are atmospheric. From here air is sucked by the compressor, and this you can see, this blue line means it is very low temperature and the low pressure. As it is entering, slowly the temperature is increasing. As you reach at the end of this compressor, you will get some green color. This green color indicates that there is an increase of pressure and the temperature, but it is not a very big increase. This you reach after compression. It is a adiabatic or isentropic compression which is taking place here. Isentropic compression, P2 and T2 here, and this P2 and T2 are higher than P1 and T1. So the objective of the compressor is to increase the pressure, but not very much temperature. Pressure it should increase very high. So if you can see this diagram here, 1 to 2 here. So here you can see that from the 1 to 2, it is a isentropic, means S is equal to, in PV diagram, S is equal to constant. So from 1 to 2, here pressure is increased from P1 to pressure at P2, P1 to P2. So how much temperature? This is the T1 and this is the T2. So temperature has increased from T1 to T2. So here in the compression, pressure is also increasing and temperature is also increasing, but increase of the pressure is much more than the comparative increase in the temperature, and the volume is decreasing. So this volume, how we can show it? Just you can see here, this is the V1 and here is the V2. Here V2 is less than V1. So volume is decreasing, pressure is increasing and temperature is also increasing. So we have reached to the point 2 in PV and the TS diagram. Now this high pressure and the high temperature gases which is existing from the compressor is going to the combustion chamber. Combustion chamber is a metallic device where the fuel is injected. For the starting point, the injection is done by the giving some electric spark. If you see your aircraft engine, the ignition time is mostly maximum 60 seconds. 50 to 60 seconds your engine should start. In this 50 to 60 seconds, fuel is sprayed and spark is given by the help of the electric current. This spark will have a very high voltage spark is produced, and this is burning the fuel. This is only during the starting. As and when engine reaches to a certain self-sustaining RPM, this self-sustaining RPM is nearly 50% of the maximum RPM of the gas turbine engine. Suppose your gas turbine engine is rotating at the maximum speed of the turbine engine is 40,000 rpm, the self-sustaining rpm may be nearly 18, 19 or 20,000 rpm. So as and when you reach to the self-sustaining rpm, a device called the starter generator, initially for 1 minute it will act as a starter. As and when the speed of the engine is increased above the self-sustaining rpm, the starter will be automatically converted to the generator, and the generator will give the power to hold the aircraft. It is a very small, like some 4 to 5 kg, this much size, this much is the length and this much is the diameter, some 1.5 feet length and some half feet diameter. A small generators are fixed, maybe the weight 4 to 8 kgs, in between 5 to 6, 7 kg weight is there for this generator. So this generator is here not shown, but I am showing here. Here spark is given for starting only. Up to 60 second maximum. The time is from 50 to 60 second. It will give the power supply, and by the giving the power supply, this as and when this high pressure and high air is coming, fuel is supplied, and this fuel is supplied by injectors. Injector means it is very high spread, very high, very high pressurized injector system is there with very small nozzles. It is like a fumes. A very dense fume is generated of the fuel, and by the help of this spark plug, here fuel is burning, and after this burning of the fuel, so if you see here 2 to 3, it is a constant pressure heat addition, but pressure is constant. But if you see, a temperature is huge amount of from T2 to T3. This T3 is a very big amount. It may be some 2000 degrees centigrade, 1800, 1900 or 2000 degrees centigrade. If you see here, it may be some 800 degrees centigrade. And here it may be 2000 degrees centigrade temperature is there before the turbine. That is why if you see the 2, 3, the pressure is constant, but temperature is increased. This high temperature of the gases, also the pressure is also higher comparing to the atmosphere, because it is P2 and it is equal to P3. So here a very high temperature gases are entering in the turbine. This high temperature gases, and the turbine is rotating with a very high speed. So the material of the turbine is the main problem. How much maximum temperature your turbine can withstand? The turbines are not able to withstand more than 2000 degrees centigrade. So we are making the turbines to be cooled down. Otherwise, the material, due to the centrifugal force, some aerodynamic and aeroelastic effect, there will be fatigue because it is always rotating. So these type of forces are acting, and due to the high temperature, the chances of the turbines are failure is going to increase. So we have to cool. So from this air, which is cool air is sucked, some part of the air is sent here for the cooling of the turbine. Cooling of the turbine. So as much we can produce the temperature and in the combustion chamber, but this whole temperature we are not able to use in the turbine due to its material constraint. So in 3 to 4, if you see, it is a constant entropy or isentropic expansion. 3 to 4, volume is increased from V3 to V4 here, and if you see here V3 to V4, the temperature has fallen down from V3 to T3. So if the V3 is 2000, this T3 may be 1000. degrees centigrade. That is the T3. So half of this thing is further in the heat rejection. This normally if you see this T4 in aircraft, this may be 450 degrees centigrade to 500 degrees centigrade. It is called tailpipe temperature. The tailpipe temperature has to be maintained within 450 degrees centigrade to 500 degrees centigrade. It means the 450 degrees centigrade, your gases are leaving the system. So this point should be this much. So from 2000 degrees centigrade here to 500 degrees centigrade, 1500 degrees centigrade is used. So how much you have more this value, that much work you will get. Because we know the work output is equal to MCP T4 minus T3. So as much you have this less and this is more, that much work output you will get. But we cannot make T4 as per our choice, because the material is going to fail. So we can reduce this in place, this T3. How much you are able to reduce? If in place of 500, if you can make 200 degrees centigrade, so net here I am going to get 1800 degrees centigrade. So 1800 centigrade is used for the development of the work. So these temperatures are very, very important, and we can see that we can do some research work how we can increase this T4 and how we can decrease the T3. As much you are able to decrease the T3, that much efficiency of the engine you are going to get. What are the methods we can use it? How we can measure this thing? In the real aircraft of the gas turbine engine, tailpipe temperature in the propeller engine and jet pipe temperature in the jet engines are always monitored by the pilots. And if the variation of this exhaust temperature is there, it means there is some problem in power generation. Engine is not performing well. The maintenance people has to see that the engine tailpipe temperature has to be maintained as per the given conditions of the manufacture of the engine. Very important parameter. And also the T4 also, it is very important, because as much you have the high temperature, that much you will get the power, but same time this will disturb the material quality and the failure of the material may take place. So we should always follow as per the designer's temperature range, and we have to use the fuel accordingly. So hope this is clear, and I have given the practical example of the real where I have worked in the gas turbine engine, especially in Arthur's 3rd B engine, which is used in the Chetak helicopter. It is a gas turbo shaft engine, and it is producing, the RPM is 33,500 plus minus 500, and the self-sustaining RPM is 16,000 plus minus 500 RPM. Tailpipe temperature is 450 degrees centigrade plus minus 50 degrees centigrade. These parameters are the real parameters which are used in the Chetak helicopter made by HL India. Now I will discuss about efficiency of a Brayton or Joule cycle. So in a piston engine, instant high pressure and temperature is observed post ignition. In GT engine, continuous high pressure and temperature persist. So the difference between the piston engine, there are 4 strokes. Out of 4 strokes in piston engine, only 1 stroke the heat is added, and only 1 stroke you are getting the power stroke. Out of 4, only 1 is taking part in the power generation. But in the gas turbine, it is a continuous process. It is not like it will go like this, like this, like it is just rotating. So any rotating engine will give the continuous process, and in the continuous process, a continuous heat will be there. In the piston engine, out of 4 stroke, only once you are getting heat, and remaining 3 are just cooling. So you can work very nicely with a high temperature also. But in turbine, it is not possible. So for the same temperature as a piston engine which is burning inside the combustion chamber, we cannot use the same materials for our turbines, because turbines are always in the same pressure and the rotation is very high. So the centrifugal forces and some different types of forces are acting, and the material will melt very fast because it is a continuous sustained temperature is present. This cycle represents a steady state flow process or a control volume process. So in this turbine or in the Brayton cycle, it is a steady state flow process, not a control mass system. It is a control volume system is considered. This cycle also known as a Joule cycle, and the practical application is in gas turbine engine or the gas GT engine. Mostly these are external combustion engine. External combustion engines, they are only for the power plants, not for the aircraft. For aircraft, we have the internal combustion engine. So it is not for everything. Only for power plant, we use the external combustion engine where we can burn anything and the burned gases are used inside the turbine. In this, heat source is out of combustion cycle, only for the power plant, not for all. In aircraft, we don't use the external combustion. It is an internal combustion engine. It gives much cleaner performance and cheap fuel can be used. So, much better performance, and the atmospheric also very clean. Burnt gases are going very less, and any cheap fuel can be used. Like in aircraft, we use the ATFK. It is a kerosene. So, aircraft turbine fuel, kerosene. This is the kerosene is used. So, kerosene is a low cost comparing to petrol and all. The cost of the kerosene is sufficiently low. Initial cost is higher than the piston engine and also has a higher speed than the piston engine. So the initial cost of this gas turbine engine is much higher than the piston engine, and also the speed of these engines are very high. So it is not suitable for it is used for ships and aircrafts, but not for the ground vehicle due to its high speed. So as of now, we are not using for the ground vehicle. But in near future, you will see that the gas turbines are also used for the ground vehicle as and when the roads are in this nice way. And from long time, we are using in ships and the aircraft. Most of the ships are operated by the turbo engines. Maximum temperature is significantly high. This is the disadvantage of this, because we are in this maximum temperature is very high. So good quality of materials is needed. Very high quality of the material. Normal steel will immediately melt at 1300, 1400 degrees centigrade. But the temperature goes to 1800, 1900, 200. So we have to make some alloys material like tungsten or some titanium alloys. We have to mix it. Then we have to make the material. So the cost of this material is also going to be very high. The engine is much bulky than the piston engine. So the size of the engine is also more than the piston engine. So these types of engine are not suitable for automobile as of now. In future, this may be possible. You people can think some new ideas, and this you can use in your ground vehicle. One of my friend has got recently award by the Defense Minister, Sri Rajnath Singh, and on the micro gas turbine engine. So anyone, if you are interested, I can share the video for that micro gas turbine engine. So we will see here that efficiency and how we can derive the efficiency of this cycle. So here, same way as I have shown in my previous one, I cannot Okay, so here we have compressor here. This is the compressor from 1 to 2. Then 2 to 3 is a combustor. Here Q heat is supplied. 3 to 4 is a expansion. Here expansion, isentropic, expansion. Here is constant pressure, heat, addition. Here is constant pressure, heat, rejection. Here is isentropic compression. Okay, isentropic compression. So these are the 4 processes which we are using here. And if you see here, I have drawn the PV and the TS diagram. So this 1 and 2 is a isentropic compression. 2 to 3 is isobaric heat addition. Here QA or QH, and here is the QL. So here 1 to 2 is a adiabatic compression, 2 to 3 is isobaric heat addition, 3 to 4 is isentropic, S is equal to constant, S is equal to constant. So here it is the 3 to 4 is a isentropic expansion, and 4 to 1 is a constant pressure heat rejection. So the same way in the TS diagram, this you can see S1 is equal to S2, and here if you see S3 is equal to S4. So here 1 to 2 that is the compressor, and 3 to 4 is the expansion, and here your entropy remain constant. So now we will derive this efficiency equation, and we know that the efficiency eta is equal to 1 minus heat rejected by heat supplied. So here QL is a 4-1 process. So here H4, here H4 minus H1. So QL is equal to H4 minus H1, and this QH is equal to H3. Here H3, this is the enthalpy, H3 minus H2. Okay, so here we can write 1 minus H4 minus H3 divided by H3 minus H2. Taking air as an ideal gas. So if other than air, we cannot use this equation here because Cp will not remain constant. So as per this, your value of the Cp will vary. So H4 minus H1 is equal to Cp, T4 minus T1, and H3 minus H2, this denominator, H3 minus H2 is equal to Cp, T3 minus T1, T3 minus T4. It is a T3 minus T4. So now we can write it, eta is equal to 1 minus Cp, T4 minus T1 divided by Cp, T3 minus T2. Okay, here it is a T3 minus T2. So 1 minus Cp we have taken out. So T4 minus T1 divided by T3 minus T2. So here we have all the temperature, T1, T2, T3 and T4. All the 4 points are here. So to find out the efficiency of any cycle, we need all the state point of the cycle. So now 1 minus, in the numerator we have taken T1 as a common. So it is a T4 by T1 minus 1. And in the denominator we have taken T2 as a common. So here T3 minus T2 minus 1. So now we have to find out the relation between T4 by T1 and T3 by T2. And so for that, we have to find out T2, T3, T4 with respect to the T1. As we have done in earlier derivation of all the Otto cycle, diesel cycle and the dual cycle. Now, taking process 1-2 as an isentropic compression, we know the relation between isentropic compression is T2 by T1 is equal to P2 by P1 gamma minus 1 by gamma. And so here P2 by P1 is equal to RP. RP is a pressure ratio. So here similarly, so we will get here T2 by T1 is equal to RP gamma minus 1 by gamma. So here we are putting RP for P2 minus P1. Now we will take the isentropic expansion. Isentropic expansion process 3 to 4. So T3 by T4 is equal to P3 by P4, gamma minus 1 by gamma, and P3 is equal to P2 and P4 is equal to P1 for the constant pressure processes. So P2 by P1, gamma minus 1 by gamma, and P2 by P1 is a compression ratio. We can write it is a pressure ratio RP, gamma minus 1 by gamma. Okay, so here we got this equation 1 and equation 2. So the right hand side of this is equal to this. So we can write here T2 by T1 is equal to T3 by T4. Further, if you see here, we have to find out T4 by T1. So this 4 I have to take here. So T4 by T1 is equal to T3 by T2. So this T4 by T1 and this T3 by T2 both are same. This is cancelled. So here you will get efficiency is equal to 1 minus T1 by T2. So the efficiencies depend upon the two temperature, not the highest temperature, but T1, that is the initial temperature, and T2 after compression, temperature. Very, very important. Means how much fuel you are burning is not matter. How much compression you are giving, that will give you the efficiency. That is the result which we can do the analysis on this equation. So we got here 1 minus T1 by T2. So here T2 by T1 is equal to Rp to the power gamma minus 1. So T1 by T2 is equal to 1 by Rp gamma minus 1 by gamma. So here 1 minus T2 by T1 is equal to 1 minus 1 by Rp gamma minus 1 by gamma. So efficiency of the Brayton cycle is eta is equal to 1 minus 1 by Rp gamma minus 1 by gamma, and this gamma for air we take 1.4, or it may be given in your problem. And this Rp is a pressure ratio from compression, which is P2 divided by P1. So this is, I think, okay, and hope you all have understood this problem very well. Now we have to see the condition for maximum work done by the Brayton cycle. Means how much work maximum we can obtain by the help of Brayton cycle. So we have how we can get expression for the maximum work done when maximum and the minimum temperatures are given. So T3 and T1, if the two temperatures are given, how we can get the maximum work done? We know that work done is equal to QH minus QL. QH is equal to Cp T3 minus T2 minus Cp T4 minus T1. So here Cp, we will write that T3 minus T2 is equal to T1 Rp to the power gamma minus 1 by gamma minus Cp, and for T4 we have got that it is T3 by Rp gamma minus 1 minus T1. So now we will take the Cp common, it is there, and now we will take this T3 term here and T3 term here. This is and this one. So this is T3 is common, so 1 minus 1 by Rp gamma minus 1 by gamma minus here Cp. This we will take here T1 and here is T1 minus Cp T1, here Rp to the power gamma minus 1 and minus 1. This we got the equation. So now we will put this Rp to the power gamma minus 1 by gamma as a x, and then we will differentiate this equation with respect to the x and make it 0 for the maximum. To have the maxima, dW net divided by dx is equal to 0. And if we differentiate this, so here we will get T3 by x square. Here, this is the x. So this will be T3 by x square, and minus here we will get only T1, because here is x minus 1. X is also become 1 after differentiation. So you will get T3 by x square minus T1 is equal to 0, or x is equal to, so here T3 by x square is equal to T1 or x square is equal to T3 by T1. So x is equal to under root T3 by T1. So to have the maximum work done, this x should be under root T3 by T1. So this is the condition for the maximum work output by the Brayton cycle. So now we will find out how much work is required. So we know that work net is equal to Cp T3 1 minus, here we can write under root T1 by T3 minus Cp T1 here under root T3 by T1 minus 1. It is 1 by, so it is under root T1 by T3. So here we will get Cp T3 minus 2 under root T1 T3 plus T1. And this is the whole root of under root T3 minus under root T1 whole square. So here you will get T3 minus 2 under root T1 T3 plus T1. And so in place of this here, we are putting this value. So we will get here work net is equal to Cp under root T3 minus under root T1 whole square for maximum net work. Eta maximum is equal to 1 minus 1 by Rp, gamma minus 1 by gamma. And this Rp is equal to, this is x, we have already assumed. So 1 minus 1 by x is equal to 1 minus under root T1 by T3. So maximum efficiency, how much you will get? It is 1 minus under root T1 by T3. So if in the question it is given the maximum efficiency, how much you will get? So this is the equation. This cycle should not give more than this value. If it is, you are getting more than this, means there is some problem in the system. So for maximum and the minimum temperature, that is T3 and the T1, we can fix the compression ratio. So if you know, we can fix how much compression ratio we can obtain for the maximum work and for the maximum efficiency. So in the next class, we will be discussing about some numerical problems on the Brayton cycle. These are the references which I have taken from the PK NOG. The second is Yunus Senegal, and from IIT Kanpur NPTEL, Dr. Mishra. Any questions you are welcome to ask. My email is ydwedi@gmail.com. If you like this lecture, this video, please like and subscribe. It will be very good if you do. Also, if you want some improvement, please comment in the comment box. Thank you, and please be tuned for the next lecture for the numerical of the Brayton cycle. We will be trying to solve 2 numericals on this topic. Thank you very much. See you again for my next lecture.
Like, share and subscribe. Hit the bell icon for more updates.